Hi, everyone. My name's Chris DeBona. I normally look after open sourcey stuff for the company, but I also help out on the NASA relationship side. And one of the things that we were talking about with the folks at Ames and at NASA was having more sort of, I don't know, what the right exchange of people back and forth between Ames and between here in Mountain View and Google. And so this is sort of the beginning of that. What we want to do is basically have a monthly or even more than that series of speakers coming over to speak about interesting topics from our friends at NASA about all of the things they work on there. And so this is sort of the first taste of that with Mike Micire.
Close enough.
We were working on the pronunciation of his last name. Apparently anything with M and an E at the end is enough. So yes. The edit distance to so many words is just very appealing to me. So he's going to talk about the Android thing. One thing I want to point out, if you want to help with this particular project, we have like a form that you can fill out. I'd say email me, but give me about a week or so. I'm still recovering from perf. Where you can, it's sort of a free time thing, where you can help out with the Spheres project, as well as with other NASA projects. I think that would cover too.
So first of all, thank you. This is, first of all, the turnout, this is awesome. I'm really excited to not only show you a lot of the stuff that we've been working on, but there are lots of smiling faces I see in the crowd that actually helped us do the things that I'm going to present here. And so I'm really kind of stoked to tell you about the cool experiments and stuff that we've been doing on the International Space Station. So I have basically two versions of this talk. One version is very managery and talks about level 1 milestones and reach goals and Gantt charts and other stuff. And I decided, because I kind of feel like I'm amongst my people here as far as the good geekery goes, that this would be kind of just a geek-to-geek conversation. And so rather than dive into a lot of the kind of managerial details, I wanted to just talk about the stuff, frankly, that makes me get up and want to go to work every morning. This is, we've been privileged to do a lot of really cool stuff, and so I'm just going to kind of tell you the story that brings us to current date, in terms of the stuff we've been doing. So I'll also add this actually works better if it's interactive, and so if I hit a slide and you have a question or something like that, just throw up a hand and we can dive into it. There's a lot of really cool details that we can get into, and so I'll skim the surface and you guys let me figure out when I need to dive, okay? So right after we did one of our first tests, actually some folks here in your production group frankly did a better job of describing this than most. And so what I'm going to do is we will start with a video.
5. All 3 engines up and burning. 2, 1, 0, and liftoff. The final liftoff of Atlantis on the shoulders of the space shuttle. America will continue the dream.
Space shuttle spreads its wings one final time.
What we're working towards is a future in which we can have robots that will take over a lot of the menial tasks that astronauts do. Our first goal for our project is to have ground controllers driving the sphere around on the space station. The sphere will take data and pictures and sensor readings and send that back to the user.
She hooks it to the front, and at that point the phone will be able to tell the sphere where it needs to go. The processor, the camera, and all of the sensors that are in the Nexus S become the brains of the robot and tell the sphere where it wants to fly. The Wi-Fi on the phone connects to the station Wi-Fi. That gets linked down to the ground, and then hopefully we're going to be able to control it from the ground.
We chose the Nexus S because the phone is very easy to take apart. Android is easy to program, we're familiar with it, and we needed to make a lot of customizations that are easier to make with Android.
Google was also working on an open source data logger, and it met our use case requirements.
You can download this application for your Android device, and that is the exact same application as what NASA is using.
The more time that the astronauts can spend doing science, the more value we're getting out of that investment.
Our goal is to provide enough value to crew and enough value to operations that they'll be able to keep it up there for a long time.
Roger roll, Atlantis. Houston now controlling the flight of Atlantis.
Okay, so hopefully that sets the stage. Now what I'm going to do is I'm going to back up in time and kind of set up how we got to where we are today. So geek test, who knows what this is? Exactly. So it turns out if you back up to like 98, 99-ish, there was a couple different groups that were, strangely enough, all of them kind of used this as inspiration. And it's the idea that if you're in a microgravity environment, can you have something that would be able to float around? And of course, the fact that it made little thruster sounds and stuff like that made it a perfect metaphor because everybody effectively knows what this is. So if you step back, this was PSA, and this was actually developed out of Ames. And it's the whole idea with this one is it was PSA stands for Personal Satellite Assistant. And it truly is, if you remember from the Flubber movie with Robin Williams, the idea that it's his little floating assistant that will go around and do things for him and bring him stuff or be able to provide instructions or things for him. And so that was one of the many, many goals that this project had. Unfortunately, that program was canceled. And around the same time, this is AirCam, which was a project out of JSC. And so this actually flew, I think it was one of the STS-73, I think, where they actually had, this is about the size of a basketball, and it was able to fly around in the back of shuttle. Basically what they did was they took the safer pack that you see a lot of the famous shots of the astronauts doing spacewalks in, and they took the human part out, compacted it down, and when it flew, essentially looks like this. And so they were able to very successfully fly that around and provide that as a demonstration of how you might have a free flyer working in space. Now this is EVA, so this is outside as opposed to PSA, which was for inside of station. Now, at almost exactly the same time, MIT had and it was like an undergraduate capstone class where they were trying to figure out, okay, can you use these small satellites for doing testing? They basically wanted to create a test bed. Because it turns out if you're writing an algorithm for a satellite or something, and you put it in space and it messes up and manages to deorbit itself, that's both frustrating and expensive. But if we can do some of those tests inside of station where you have an astronaut there that can grab it if it starts flying off and doing the wrong thing and be able to reset and kind of iterate, that there would be a lot of value in that. This is a bit of a Cinderella story because it truly did go from being a project that students were working on to fast forward 10 years, and this is basically what we have now. There are 3 of these on station. We have, I believe, 4 of them on the ground, and one of them lives over at Ames. And we have a whole lab where we use this day in, day out for a bunch of different projects and a bunch of different science that we're trying to do. Just briefly diving into some of the semantics here. So the way the spheres work basically is there's a CO2 tank that plugs into the bottom of it. This is a CO2 tank exactly like what you would use on paintball guns. In fact, whenever our CO2 bottles end up getting low, we've had situations where we didn't have resupply, and we actually will go to Sports Authority and have them refill our. And of course, they say, "Is this for a paint gun?" And we're like, "No, it's for a satellite." And they're like, "Oh, okay." So basically, the CO2 tank, it's liquid CO2 that's passed through a regulator. The regulator then puts it through a tubing basically inside that goes out to these little yellow thrusters that you see, and there's a little solenoid on each of those thrusters. And so what the computer inside is able to do is it will just activate each of those solenoids, and that's how it releases the thrust. There's also ultrasonic receivers on the outside that I'll talk about in a second, because it's one thing to be able to move yourself through the environment, but to do that meaningfully, you have to know where you are. And so that ends up being one of the difficult tasks. If you pop the hood on it, it turns out that it's basically an aluminum frame in which we pack an insane amount of electronics and sensors and other things into. Basically, one of the things here that's kind of interesting is for these, it actually uses alkaline battery packs. And so we have part of our job as far as maintaining these is we end up resupplying AA batteries basically for these satellites. So I mentioned, and I'm not going to go too much into the details here, but basically the way the sphere figures out where it is it's floating in the middle of a 6 by 6 by 6 foot volume. Okay? The first thing the sphere does, it has these little IR transmitters on it, and so it sends out an IR pulse, and you can think of that as starting clock. So it starts clock, and then there's 5 beacons, and on 20 millisecond intervals, they have ultrasonic transmitters that begin counting off. So start the pulse, and then 1, 2, 3, 4, 5. Each of those will do a click. Now, the sphere I mentioned before has these little ultrasonic receivers all the way around the outside of it. It turns out that if you consider the first pulse to be the speed of light, which is really fast, the speed of sound is relatively slow compared to that. If you do the timing from the beacon to the satellite, you can actually do some math, basically do some triangulation and figure out where it is. That plus a Kalman filter gets us within a couple centimeters of where the actual position of the sphere is within the 6 by 6 by 6 foot volume. So it's great in the fact that it has a really, really good and accurate idea of where it is. The kind of downside is that in a given module, this is basically the only place where we can fly, because if it gets outside of that right now, it just doesn't have the sensing capability to figure out where it is to know where it needs to go next. What's cool is when they're working, this is what it looks like. Now, I will admit, this is sped up by about 8 times. So although they are awesome, it is a bit like watching grass grow. The cool part, though, is that the astronauts love these, and actually we never have any problem. Once we can get crew time, they're usually very excited to play with these. And you can see I actually love Don Pettit's little toes are just wiggling. And if this doesn't get your little geek heart going, you may want to go ahead and leave now, because at least for me, it's very, very cool. And by the way, if you haven't, look up Saturday Morning Science with Don Pettit. He's a pretty amazing geek, and he will change, frankly, the way you look at the world. So let's then step into human exploration and telerobotics. And I'm not going to go through these in any great detail, but just say that right now we live in a world where, at least when I leave in the morning, I reach down and kick the little on button on my Roomba, and by the time I get home, my house is vacuumed. You know, Google is doing amazing work with the autonomous driving cars and other things. We live in a world today where we're beginning to expect robots to help improve our lives and the things that we have to do. Our motivations are exactly the same, but in the context of the ISS and space travel. So right now, for the crew that we have on station, crew time is not only extremely valuable, but crew there's so much upkeep and other maintenance type things that they have to do that sometimes the science has to take the back seat. And so anything that we can do that helps them get rid of some of those menial tasks, or helps ground controllers not have to directly involve crew, or improves the communication between ground and crew, is all just huge value that we're bringing to the resource of ISS and any future exploration that we do. There's in this picture, one important thing to see here is that we have the spheres, and we're using those as kind of our platform, our test bed. And there's really 2 ways that we're feeding this. It's not only crew being able to control a robot on station, but it's also ground controllers being able to work with this. And these end up being 2 dramatically different situations, because when you're on the ground, you have huge time delays. So it's not just going to be like a radio control car where you flip the switch and suddenly you're piloting it around on station. There's a lot of really kind of smart software that has to go into those spheres to make that workable. The other thing is, if any of you ever want to come over and try to fly a sphere even in 2D we have a granite table where we can fly it around. The fact that, like with a radio control car, if you take your hand off the stick, friction and other things will eventually cause that little car to come to a stop. As someone who grew up with radio controlled cars and airplanes and other kinds of stuff, it was humbling to try to control a free flyer in a frictionless environment, even in 2 dimensions. And so even if you wanted to, you're not just going to have somebody joysticking this thing around. So we said, okay, the Spheres is an amazing platform. We have lots of capability here, but one problem that we have is the CPU that is in that thing is already pretty busy doing the math of triangulation, and it's about a decade-old processor at this point. So it's an old TI DSP running at about 170 megahertz. Amazing in its day, but by today's standards, a little difficult to work with. And so we were like, all right, well, we're good geeks. We'll just upgrade it. Upgrades are the way to go. And so, believe it or not, we didn't start this project by saying we are going to put an Android phone or a smartphone in space. We laid the kind of the trade space up on the whiteboard, and we said, okay, well, it's going to need to be small. It needs to be power efficient. It needs to have integrated sensors, low power. Have of course, you know, it would be cool if it had like a Unix-like operating system on it. And we laid all this up on the whiteboard, and of course, we're all sitting there checking our emails. I don't know where we're ever going to find a device that satisfies all of these requirements. This is impossible. And what we realized very quickly was that a smartphone would be a very, very good way to attack this problem, as opposed to trying to roll our own. Now that's humbling to say that even NASA cannot outrun the technological advancements that are happening in the mobile phone market today. That's pretty crazy. Yeah, question. His question was, how fast are the control loops? And I'm assuming you're talking about for the actual spheres themselves in terms of their flight. And the answer is there are multiple, you have multiple threads that are running. And so let's just, I don't know them off the top of my head either, so we can geek out after we'll take that offline. So, all right, so we basically said, all right, well, a smartphone would be a really great way to do this. And like I said, NASA is even having a hard time outrunning the advancements that are happening in the mobile phone market world. And now the question was, well, you know, what could we do to make this work? And your trade-off between building your own versus buying COTS is that if you buy COTS, whereas on the one side you have a lot of engineering that needs to happen, on the COTS side you have a lot of reverse engineering that needs to happen. And it's a little tricky when you go to Samsung, for instance, and say, hey, what does your accelerometer do in microgravity environments? And they're going to smile and go, well, you're NASA, you tell us. And so there was a bit of a risk that we kind of had going into this. And frankly, we had no idea of the many risks that we were accepting by going down this route. I throw this up. I'm actually going to come back to this slide, but what I'm going to do is talk through some of the flight barriers, basically, that we had. When you put something on a spacecraft in orbit, you have lots of kind of gatekeepers and flaming hoops you have to jump through to prove to NASA and the safety guys that you're not going to cause problems on the spacecraft. And so what I'm going to do, I'm going to dive through actually a subset of these and show you some of the hacking. It's not only hardware hacking, but software hacking, and in a final case, even social hacking to kind of make the whole thing happen. So let me first begin by saying God bless the internet. Because what happened was we had talked with a couple other groups that were using one of the Nexus 1 phones, and there were just some barriers they were having to climb through that we were like, well, the Nexus S really seems like the phone that we probably want to fight with. And I fix it somehow prior to, about a day or so prior to the release of the Nexus S, managed to do a teardown. So we immediately said, all right, well, let's start looking at what this thing's got. And one thing that we were told very early on was that we had to hardware disable the cellular phone functionality of the phone, for the same reason that when you get on an airplane, you have to either put it in airplane mode or physically turn it off. It turns out the ISS has similar rules, and it's pretty much all the time. It needs to be in an airplane mode. And we told them, we said, well, in the kernel, we can completely disable the phone's ability to talk to the radio. We'll guarantee that there's no way that this radio can be activated. And unfortunately, the comeback was, well, no, actually, it needs to be a hardware disable. You have to have a hardware switch or some way of physically making sure that transmitter can never fire up. And we were like, okay, well, I guess then one way of doing that would be to pull basically your TX front end which this is the cellular phone part of the phone, and we were pretty sure that if we could disable that chip, that we would be able to pull that off. So myself and one of my other engineers actually camped out at the Best Buy up at Rangsdorf, and I think there were 13 phones that were delivered to that Best Buy. We got numbers 11 and 12. Immediately took it back to the lab, completely pulled it apart, and laid it up on a heat bath. I don't know, basically what this does is, you can think of it like a crazy hairdryer blowing upward, and the whole idea is what you want to do is you want to heat the board, and then this is an air pen, and we knew that this chip was a BGA, which means it's soldered on the bottom. And unfortunately, with it being a BGA, you're not just going to take an X-Acto knife and cut the enable pin and have it work. So we said, all right, we've got this. We're going to own it, and we failed epically. I laid this up under the microscope, and it looked like a tiny little Civil War battlefield. There were capacitors and resistors just strewn all over this. But I'm a big fan of fail fast and fail often, and so we were like, all right, well, we've got 2 phones. Let's screw up a second one. And the important subtlety to this presentation is you can see actually this is now glowing red. So we're like, well, let's burn it up. Worst thing we can do is ruin another phone. And so the cool part was we actually managed to figure out a way to lift that chip. And we got pretty good at it to the point where you could pull it, you could clean it up under the microscope, and the phone is none the wiser, luckily. It just thinks it's sitting out in the middle of Nevada somewhere with no signal strength, and it just kind of quietly sits there not getting cell phone access. The next thing we needed to figure out is we were told lithium ion batteries were very, very hard to certify to get on station. It has to do with the way that lithium can sometimes go supercritical depending on what you do with it. But we were told if you go alkaline batteries, if you go AA batteries, that works. There's so many things on station that run off of AA batteries. You hear the metric of how many dollars per pound it costs to lift something into space. I don't ever want to do the math on how many AA batteries we resupply to space station. So it was like, okay, so let's find something that'll hold AA batteries. Luckily, I think Adafruit was where we got this space certified battery holder. We basically sourced a battery holder. We had already done some other projects with this little guy, which is basically a DC to DC switching regulator. And the important part is it's got this little adjustment knob on the front of it. And we figured, all right, well, we'll feed it with AA batteries, and then we'll let this little switching regulator fake the phone or trick the phone into thinking it's got a lithium battery. It's important to make sure that you don't charge the DC to DC, though. So we threw just a simple little diode in there. We basically ruined the back of another Nexus S phone and figured out how to cut all of this out so it would fit. And then started doing some testing. And this is another just kind of get it done moment where it was like, well, we could instrument this whole thing where we were logging the voltages and stuff like that. And so what we ended up doing was just taking a phone, putting it on time lapse, taking pictures of 2 voltmeters until the phone went dead. And then took all of those pictures and hand entered them into a spreadsheet. Now there's important subtlety here that you'll see why it's important in a second, in that in this case I'm actually taping the phone to my laptop because I didn't have anything else to stand it up against. And there was a moment where I was like, well, actually I just taped it to my laptop. How am I going to push the buttons? And it turns out you can push buttons through tape, and so the whole thing ended up working. And the good news is we were able to fake a phone into basically running off of AA batteries. We can get about 7 hours out of it. And the important part here, this is a lot what lithium ions cruise along and then drop hard in the end. And that's frankly why everybody that does digital electronics loves them, because it'll hold a reasonably constant voltage for a long time. That's what an alkaline does. And so basically the DC to DC ends up being a great little tool for us. So the other thing that we were told was, you've got glass on the front of this phone. What happens if an astronaut decides to fast pitch it and it goes into the corner of some handrail or something, and he breaks that glass? And now you've got little shards of glass. We break glass here on Earth, and the glass falls to the ground, and everybody goes, ooh, don't stand near the glass because you might get it in your feet. And microgravity, though, those are little shards of things that you may breathe. that ends up being a much more significant hazard. And so we were told, all right, you need some way to contain the glass. Now, luckily, I had already accidentally figured out that clear acrylic packing tape that you can touch the capacitive touch screen through that. It kind of makes those $20 screen protectors at Best Buy seem a little expensive, doesn't it? Now, pretty much for all my screen protectors, I just lay packing tape over it and then take an X-Acto knife around the edges. And that's basically what we did here. It turns out that acrylic tape is considered flammable by ISS safety considerations. So we actually ended up using Teflon tape because we had actually done it all up in acrylic, and they were like, no. So, of course, once you do it, you have to test it. And so we destroyed another perfectly good Nexus S, but it was for science. And the good news here was we were able to basically contain the glass. So both of the phones that we actually flew are covered in this tape, and you can pretty obnoxiously damage the screen, and of course it keeps all the glass intact. And when you get it all put together, this is what it looks like on a sphere. Basically, we Velcro it right to the front. As Han Solo said, it doesn't look like much, but it's got it where it counts. And what this did was we basically flew these on the last shuttle that went up. Now, there's an important point here, and that's that with all of this amazing hardware hacking and other fun stuff that we were doing, we knew we were going to come right up to the wire, and we had no software written, which would kind of be the whole point, right? Well, it turns out that luckily we were already kind of talking to actually some folks that are even in this room. And you had a group here, the Cellbots motley crew, as I'll call them, that were already working on some really cool apps that were enabling robotic-like interaction, but using Android. And so we ended up having this wonderful collaboration in figuring out how to take this open source logger and allow it to then run on station. This gets back to the whole question of going to a sensor manufacturer and say, what does your sensor do in microgravity? They are going to almost drop the phone laughing at you. And you also have to remember that a lot of these sensors are born out of other places. So like the accelerometers that we use, a lot of that technology actually came out of the automotive industry, where it was for deploying airbags in very high G environments. So we had all kinds of questions of, will these sensors have the sensitivity that we need to provide the information that we want? So this ended up being a kind of a great addition and ended up being one of the first tests that we ended up doing with the phone. So let me circle back and talk about some of the barriers. So the first one, procurement and certificate of conformance. Real quick, a certificate of conformance is basically, let's say you're some Aero-Astro company, and I say, I need a flux capacitor, and I need it to conform to the following things, and I give you a set of requirements. And then you run off and you build me a flux capacitor, and then you come back with it, and you say, here's your flux capacitor, and here's a certificate of conformance that says that this conforms to the following requirements that you gave me. That's required for virtually everything that flies. Do you know how to get a certificate of conformance for a Nexus S that you bought at Best Buy? Right? The answer is you show up 5 minutes to closing, you go find the manager, and you basically hand him a piece of paper that says, hi, I'd like you to sign a piece of paper that says that a Nexus S is a Nexus S. And he will look at you cross-eyed. And the good news is you can actually get him to sign it. And we ended up doing this, like, for instance, for the battery holder. I don't think that Adafruit had ever worked with anybody who needed a certificate of conformance for a AA battery holder before. And so that was the one thing that we found is the process that we use wasn't quite tuned for the kind of cool hackery and other things that we were doing here. I talked about disabling the cell phone part and the batteries, the glass breakage was a problem. Mechanical drawings, it turns out if you go to Samsung and say, hi, I would like the full CADs and schematics for your phone, can I have that? And so we basically ended up having to kind of generate our own mechanicals for all of this. The last one, or the second to last one, the Windows, so here's a cool fun fact. All of the laptops that are up on the International Space Station right now are running Windows XP Service Pack 3. Do you know what happens when you plug a Nexus S into a Service Pack 3? Luckily, no. Unfortunately, it starts asking you for drivers, of course. And unfortunately, to get a driver certified for use on one of these laptops on station is a multi-year Gantt chart. Basically, we looked at certifying a driver, and it was longer than our whole program. And we were like, okay. So what we basically did was we ended up building our own firmware for the Nexus S, where we were able to allow the phone to kick into mass storage mode before it was ever plugged in. I'm sure all of you know you have to plug it in before it asks you if you want to put it into mass storage mode, because basically the UUID for the mass storage device, Windows XP Service Pack 3 liked, whereas the serial port or the USB multiplexer that was on it would immediately kick it into, I'm Windows and I don't know what you're plugging into me, and please hit OK or tell me where to go. And so we were able to go through and basically modify the OS to our needs, which was really important because that would have been a non-starter. And we didn't figure this out until the 11th hour, almost literally. It was at the end and we plugged it into one of the test laptops and it's like, driver disk, and we all had heart attacks simultaneously. And then also, like I said, we had no time for software development, and this is where a lot of the folks in this audience and with the Soulbots group were able to help us out and backfill that. So we actually had the phones built. I love this picture because I think the packing instructions were more complicated than anything we did prior to that.
I have a question about the phone issue and the USB.
Yes?
Why did you need to plug it in USB at all, given can you use the Wi-Fi?
So actually, very early on, we were not cleared for using Wi-Fi. The network on ISS, of course, can't call out to the internet. And so we had debated the idea of, well, could we like load the APK through like an ADB over Wi-Fi? And basically what it came down to was the shortest path was for us to, we basically uplink the APK to station. They put the phone in a mass storage mode. We copy the APK over to the SD card on the phone. And then we have basically an app on there that'll do a local APK install. And that was the shortest path basically to get us through to flight. So we're actually now going back, and frankly, now that we know a lot more about Android than we did originally, we're going back and revisiting that whole process. And it would be very cool to be able to just load it over the Wi-Fi. So it went up on 135, which was really cool because we know. So for myself, not only being able to know that my team had cool little stuff sitting in the back of that pickup truck, but we also got to go down there with a lot of the folks that helped us to build this thing out. Yes. We'll get to that in just a second. So the question was, does the phone connect to the sphere? And it would be very anticlimactic if it didn't. So Atlantis, basically, they passed it into ISS. And actually, I was just reminded that the anniversary of this is pretty much a year ago today. This is the sphere with a phone stuck to the front of it, flying around on ISS. And this is what it looks like. This is, again, sped up for your viewing pleasure. But you can see that the phone's kind of stuck to the front. And what this is doing is the sphere is running through a series of maneuvers that are allowing us to log basically what all the sensors are seeing. So we didn't know if the accelerometer was going to have enough sensitivity. We didn't know if the gyro was going to be able to detect the change in movement and such. And so this was kind of our acid test. You'll also notice, I apologize for the video quality. Hopefully this will load. There we go. We were having a bit of a problem with the sphere that day with it resetting, and it had to do with the IR mechanism I was talking about being jammed by the lights that are on station there. It turns out when a fluorescent light begins malfunctioning, it emits a lot in the IR spectrum. And so we basically had to turn the lights way down. And so what you're seeing here is this is the view out of the camera, and this is me doing some gorilla image processing to bring the light levels up. And so the good news is that, at least in terms of camera performance, even in low light conditions, that we're able to kind of see artifacts and figure out what's going on and where it's flying. The gyro, we smiled because, so what we've got here, so this is the test on the ground, and this is the test on orbit. And each of the little kind of edges that you see here, that's a thruster firing. So you're actually seeing the change there. And the good news is, based on what we see on the ground, where we can only really move in a 2D plane, we do have enough sensitivity in the gyroscope to be a useful sensor to us.
How well did the compass work?
This is the one that surprised us. We did not expect the compass to be useful. We're like, I don't know, what does the magnetic field look like in orbit? I'm sure it's there, but what does north mean when you're going 17,000 miles an hour in an orbit that is like this, right? North becomes very relative. But to our surprise, this actually is working a lot better than we thought, and we're actually investigating using this because there are ways, of course, for us to know where ISS is in orbit. And so if you can come up with granted north moves for you, but that may tell you, even in the base case, may tell you interesting information like where is the floor? Sometimes for a robot, that's an important question to begin with. I don't need to know my absolute pointing, but if you can just tell me where the floor and the ceiling is, that allows me to bootstrap some of the higher level algorithms that I might use to begin localizing myself. So this is one that frankly we have very important people working on this right now.
Are there other scientific instruments with magnetometers doing any sort of science stuff?
Yes.
Okay.
And so we are actually working with actually a couple different groups. And what's kind of fascinating too is we have talked with other research groups within NASA that were surprised about this too, and now are talking about possibly rolling smartphones into other products that are not even robotics related. They're like, wait, you can get pointing out of that? That's very cool. The gravity sensor, turns out, couldn't detect gravity, which is good. That means, we didn't fake this in a soundstage in LA. So that was kind of fun. The bad news is, unfortunately, the accelerometer just doesn't have enough sensitivity. It ends up being a lot of noise. And we're actually looking with a couple different folks at seeing if we can pull signal out of this. Now, that's kind of the bad news. The good news is the spheres actually have really, really, really good accelerometers already inside of them. So this would have been kind of a freebie if we could have used the phone's accelerometer. But sadly, at least it looks like right now that won't be a sensor that we'll be using. So we then said, okay, well that tells us, that gives us a baseline as far as what the sensors can and can't do. So we said, let's look at what the network's going to be able to do to us. This is a very, very simplified drawing of basically ISS down to building. This is building 30, which is the Mission Control Center in Houston. And basically, we have a workstation that's down there that we can sit at. And the question was, how do you get through all of these pipes and up to the top? And so what we first did was, because the code that we were running was written in Java, we were able to take and basically port it over to normal Linux Java install, and we remote controlled a PC and emulated a phone and made sure that we could talk from station all the way down to the workstation that we had there. This is actually us sitting in, it's basically an engineering back room in Mission Control, and those images, believe it or not, even though it's a video of on the ground, those images are actually coming from the space station. And I apologize for the shaky video. It turns out it's really hard to record things and take them out of Mission Control. And so the way that we capture most of this is me standing there with my smartphone trying to be as still as possible, videotaping the screen. And this was able to show, we basically had echo tests and other things that we were running, and that kind of gave us a really good benchmark of what was working and not working. The other important part here is this isn't just us. There's actually a whole team that is out at Johnson Space Center that helps us. And so what was really fun is that after we got out of the kind of geekery and engineering that we were doing, we found out that there's this whole other kind of extended family that we have out there that's helping us get a lot of this work done. The thing that was really cool about after this experiment was we got an opportunity to walk out on the floor of Mission Control and talk to the flight director, who immediately was like, what you guys are doing is amazing work. I want basically Google video chat on a robot as soon as you can. And it was pretty validating because frankly, up to this point, we knew we were doing good science, but it's just nice when folks that are doing the hard work, that are there at the consoles, come up to you and say, this is cool, this is value, can you please continue doing what you're doing? And so to have the flight director for that orbit basically say, I want video chat, I want to be able to chase astronauts around, and the big thing, and if you watch NASA TV a little bit, and you see the way like the cameras are set up, and you'll see astronauts flying around and doing stuff or whatever, that's great. But what's really tough is when that astronaut's working on your experiment, and you need that kind of over-the-shoulder view. Right? And what they'll do is you'll spend the first 15 minutes of any crew interaction setting up the camera and getting it in place, and then the astronaut will go down and immediately get in front of the camera and begin working. And so, especially for the ground controllers, that's huge to be able to nudge that camera slightly and get a view, or to go look at that panel that's got the red light, you know, and kind of figure out what's happening there is just bring huge value to these guys. So. Then it was on. It was like, okay, let's use the phone. And the big thing that we were testing here that was different before was we had the actual smartphone, and it was connecting over the wireless access point. Okay. The tricky part here was, like with any wireless network, the wireless access point isn't in the module that we're working in. And we were told repeatedly, it's like, oh, well, it's in the next module. You'll be fine. The laptops use it all the time. And I kept having to remind the engineers, it's like, okay, your Livono T61 laptops have this huge antenna that wraps the screen. Our antenna is about this big, and we put a giant 6-pack alkaline battery thing on the back of this thing. You know, depending on which way this thing's turned, we're attenuating that signal pretty significantly. The good news is we were able to fire this up, and basically that is an astronaut cruising around with the phone just unceremoniously stuck to the wall. And we ran this test, and we're able to show that we're not only able to get through all of the tubes that we have to get through, but that in terms of Wi-Fi, actually this was a more difficult Wi-Fi connection than what we expect to see when we're in the module that we normally work in. So we're good on Wi-Fi, and that was the important part. Then, to your question, now that we've tested comms and we've tested sensors, it would be nice if we could actually tell the sphere where to fly. And so we ended up building out this, it's basically a USB cable that's going to a level converter inside, and that's connecting to an expansion port that's on the sphere. There's an important distinction here in that we are not using this as a USB port. The Nexus S, as you may know, has the ability to you can kick the USB multiplexer into a serial port mode. And so because the sphere only supports serial and not USB, we actually use this as a serial port and then use a custom protocol to talk to the sphere inside. That went up on one of the Soyuz resupply missions, and this is what it looks like. So basically just extends it a little bit, and then with the level converter kind of tucks in between those two plates there. And this is an expansion port that sits on the front of it that crew can basically, we are one of many experiments that use this expansion port for hooking things up. The problem with being a roboticist is the customer never wants what you build. And so what this does is it allows customers to come to the table and strap their sensors to the front. I showed this not to explain it, but just to say, when you're in orbit and you have a lot of time delay, and we have this I'll call it a problem, called loss of signal. And that's where, for sometimes 30 and 45-minute windows, we have no communication with the ISS over the network that I showed you. It's just disconnected. And so what we have to do in software then is make sure that we are compensating for all of these different situations that can arise. So this is the user interface that we're going to be using. We're hoping to actually get crew time in like late November, early December. And what we're able to do, this is an interface that allows us to kind of set up plans that the spheres will execute. You say, Mark, why is there a cat? All right, now, so imagine every time you see a cat, that's going to be a view from the phone. What we figured out, and this was a social hacking, one of our colleagues that works down at JPL has figured out that if you can sneak cats into your presentation to the safety guys, it calms them. And you don't get really, really hard questions, hopefully, afterwards. So it's actually become a challenge at this point. We try to sneak cats into our interfaces as much as possible. So basically, running very quickly through this interface that we developed. So basically, first we verify that we've got a connection. The neat part here is we're able to we basically create these plans, and what the plans do is they tell you, I want you to orient a certain way, I want you to fly to a certain position, I want you to turn on the flashlight, I want you to take a picture or start recording video. And so we've kind of come up with basically a recipe or a plan that the Spheres is going to execute. And then we have these 3D views, which allows us to preview what we think the Sphere is going to do. Once we've previewed that, then basically, this would be the image that's actually coming from the Sphere, and you basically see the progress of where it is. And again, the 3D views, whereas before it was kind of predicting or giving you a simulation of where the Sphere was going to be, this is actually live telemetry. So this is pulling the position information back out and then rolling it into the display. Then, no good plan survives first contact, and that's especially true for robots. About the time you think you've got all the combinations figured out, the universe will throw you something that you didn't think about, and you've got to go in and do some manual adjustments. And so what we've done is provided a way to do manual control. Now, this isn't like rate control. This is basically, we call it nudging. So if you tell it to go and you want to look at a panel, or you want to position it in a certain way, what you do is then you can nudge it slightly and just kind of move it in very small increments left or right, because you've left, right, up, and down on all of its different degrees of freedom. And you have to remember that you've got significant time delay between you and the spacecraft. And so what this allows you to do is kind of go through and do some nudging and reset things. And like I said, all of that's then kind of displayed up in the 3D image. And that kind of brings us to current. So that's where we sit today. Like I said, we're hoping that in late November, early December, that we'll get some crew time. And what will end up happening basically is myself and some of my engineers will be sitting at consoles. This will be running on a laptop. And we have a whole series of plans where we will be uploading these scripts to the phone. The phone then ends up kind of enumerating all of the plans and figuring out how to turn that into Sphere speak. And then there's a program that runs on the Sphere then that starts executing all of these things that are thrown there. So let me end by first saying thank you to the Cellbot group and all of the folks here at Google that have helped us. None of this that I've shown you or in the future would be happening without you. And to lay a little bit of a teaser, a kind of we want you kind of thing in here is this is continuing, and I don't expect this project and similar projects to go away anytime soon. We are definitely generating interest within NASA. Folks seem to be seeing value, and the thing that we have now is we're getting a lot of work, and most importantly, a lot of really interesting, geeky problems that we would love to share. So if you like kind of cracking hard nuts and figuring out how to make phones and sensors do things that they were never designed to do, in environments that are very, very cool. Either that's my email address, or basically contact me and we'll find a way to get you rolled in. So thank you very much. Are there any questions? Go for it. So the question was, how does the Sphere outside of station figure out where it is? That one was actually rate controlled. So that was a joystick that was inside of shuttle, and they were watching the video on it and actually rate controlling it from inside. Now, because that was being controlled from station, it's a very low latency radio link, and so it did not require the kind of positioning that we were looking at. Yeah. It does. So the question was, does the CO2 that we release end up affecting the CO2 levels on station? And yes, it does. It's not, well, let's put it this way. The engineers, when they first, back in 2006, when they flew this, it was basically they figured out that the scrubbers are more than capable of handling the CO2 that this ends up releasing. But there are like some flight rules basically that we have that make sure that we're not releasing too much CO2 into that environment. So. Yeah, so okay, so the question was with respect to the zero-G flights or the vomit comets. Yes, so actually the photo that you saw there with the MIT students, that was actually on NASA's vomit comet. There are follow-on projects that have done the commercial zero-G flights. We have, so not only that has been done, we also have both out at MIT and at our lab over at Ames, we have a large kind of polished granite table that allows us to float the sphere in 2D. You can kind of think of it as an inverse air hockey table where the puck is able to levitate itself using CO2 being forced down and creates a frictionless 2D environment. To do that, we also have software simulators that are able to do a pretty good job of demonstrating the physics that we expect to see in microgravity. We go through a pretty exhaustive process of making sure that the software is going to do what we expect it to do before we start burning crew time, because that's the most expensive part of this whole equation. What we don't want to do is have crews set it up and then we haven't done our homework to make sure that it's going to do what we expect it. So the question is how much of the navigation is kind of handcrafted versus being algorithmic. Right now, at least with respect to the control that we're doing with the smartphone itself, it's basically waypoint navigation where we're able to tell it go to this coordinate, turn to this pose. And then it's actually figuring out the thruster mixing that it needs to do to get from point A to point B. For any given orientation, it's got to do the math of figuring out what combination of thrusters and timings it needs to fire to get there. There are ways of actually having it go to more of I'm following a path or a vector through that space too. There's been experiments that frankly we're not using just yet, but there have been investigators that are actually looking at, okay, if I have this configuration of obstacles, how with the thruster configuration I have, can I optimize this path? And autonomously, make sure one of the big things for free flyers is fuel. How do you get from point A to point B and make sure that you're going to be able to minimize your fuel usage so you can get to point B? Because unfortunately, again, unlike on Earth, when you run out of fuel and you're moving, you're going to keep moving. You don't eventually come to a stop. And so there's actually been some really great research that frankly we get to just stand on the shoulders of those smart people that have figured out how to do those kind of things. Sure. So the question is, and I'm going to summarize here, is basically we've changed the center of mass for this satellite. And really the important subtlety to that is the mass that we've added to it is outside of the thruster volume. And so right now, I don't know if you noticed, but in the video that I showed where it was the low light video, if you watch that video, it actually lobs a little bit. So when it takes off, you actually see the phone angled down a little bit. And that's because for that test, the sphere was almost literally imagining, in terms of its modeling, it thought that it was a perfectly spherical cow. Like it really did think that mass was equal on all sides. The good news is that basically between our group and MIT, we've been able to tune the algorithm that it's using to adjust for that. There's actually a project that is separate from the smartphone one that has a much more massive sensor that it's putting on the front of it. And they've been doing the hard math of, okay, how do you not only model the change in center of gravity, but then the fact that center of gravity in that case is probably almost pushing itself outside of the thruster envelope. And that's hard math that I won't even pretend that I know how to go through myself. So the question is, what do we do on the phone versus the controller? So as roboticists, we like to look at things like motor controllers and think of that as like a black box. I've got this high-level algorithm and it's just providing a vector, and then somewhere down below in the layers below, it's figuring out how much to actually apply to that H-bridge or that whatever. The sphere to our project effectively ends up being like a motor controller. We feel very fortunate that we can tell it things like go to XYZ and turn to the following pose, and it will figure out the thruster firings and other things to do for us. So that's really kind of the divide, is that you can think of the sphere as doing all of kind of the hard avionics side, and the smartphone side of it as working the higher level, a lot of the camera sensors, the Wi-Fi, it's your communication path. And the really interesting part for us, and this changes the way, frankly, a lot of NASA's projects has gone, is it allows the software to be the science. in that we can work on those higher level algorithms and know that there's this solid base that's down below us that's basically doing the avionics and the flight part very reliably. So the question is, what kind of sensing is done on the sphere? And the sphere has accelerometers and gyros on each of its axes, and the ultrasonic positioning system that I described. So it knows where it is, and it can sense motion, and that's it. There are no cameras. There's, at least in the base configuration, that's all it's got. And so that was one of the big values, frankly, that the phone was bringing for us, was between the camera and the Wi-Fi and everything else we wanted to add on. There was just a lot packaged in that little box. The question was, does the sphere give information back to the phone? And yes, we have a telemetry stream basically that we monitor, and that is what's communicating to the phone in the plan that I described there. That's how we know, okay, it's reached this point in the plan, and now we're moving on to the next point. So it's out of that telemetry stream that we're able to figure out that we've succeeded in whatever that sub goal was. So the question is, can we use this, I'm assuming as kind of a litmus test or a test point for future satellites? And the short answer is yes. This is, frankly, a technology demonstration for NASA and all of the folks that are working in these kind of environments. And so our hope is to not only be able to demonstrate, but be able to walk away with this for, okay, here's your best practices that you want to try to tackle. You know, here are the capabilities. If you're going to, let's say, choose a smartphone or some type of COTS device, you know, here's the level of capabilities that you're going to have to hit to know, you know, what you're battling in terms of, you know, what the sensors are going to do and stuff like that. So it's a good data point for us. It'll be interesting to see how many other projects end up kind of globbing onto this idea. Like I said, but I have other projects literally calling me probably weekly, wanting, just after hearing about this, wanting to know how we were able to use these smartphones and what it took to make them work. So there's definitely interest. It's left to be seen, though, whether we have other projects kind of getting on board. Of course, the question is, are we going to upgrade? And right now, frankly, the Nexus S is a great phone for us, and we know it cold, and that we're fully up under the hood of that phone and know it very, very well. We have other projects that are hopefully coming along down the road here, and of course we're going to go into that with the same kind of open trade space that we did before and say, okay, we've had a couple years go past. Does it make sense now to throw a Panda board up there, and then lay up the leading smartphones and try to see who's got the best in class for the kinds of things that we need to do? We're kind of mercenaries in that, you know, we'll just lay up the requirements, and whatever can fill that gap, we'll go with it. And so that's left to be seen as to what phone we actually end up using. The question is, do we use the screen? And initially, you know, when we first started doing this, actually the screen really wasn't even on our list of requirements. But as you probably suspect, the ability for the astronaut to be able to go up and interact with the screen, or to start recording, or to enable the phone's functionality in some way, or do something simple like configure an IP address. Or dismiss a forced close error. Lovingly. Which actually we've done that with our own code also. So,
now that you have front-facing cameras, you can use it as a flashlight for your low lights.
Yeah, so the comment was, now that we have front-facing cameras, and actually in this case, what was kind of the downer was, because the big battery pack is stuck to the back, really the high-resolution camera and the cool flashlight are hidden behind there. And before we flew it, we actually thought, you know, it'd be really cool if we could periscope that, like 2 front reflecting mirrors, and we can do the double bank shot, and get that out the front. And unfortunately, we just didn't have time to do it. Would definitely, that is in our requirements list for any improvements that we do moving forward, is not only getting the real flashlight. Right now, we do the old G1 trick of, we just make the screen really bright and white. And so we'd like for the future projects to actually have a proper flashlight that allows us to illuminate. Because as you can see, we have instances, and we didn't expect this, and this would have hit our requirements list, but sometimes we have to run in low light. And that wasn't something that we had really expected, at least for these preliminary experiments. So, all right, any other questions? All right, well, thank you very, very much. I really enjoyed this.